Today's experiment is on static equilibrium. It's page 19 of the lab manual. So if you please open your lab manual to that page. And this talks about two things that we have to worry about. One is the forces, and with static equilibrium, all the forces have to be equal to zero. And also all the torques acting on an object have to equal to zero. So there's no acceleration involved. No acceleration, no motion. Well, there could be motion, but no acceleration though. So you have a very simple example right here. You have a mom and her baby on a seesaw. So there's the seesaw. Let's say the baby's worth about weighs about 50 pounds. And let's say the mom sitting on this side weighs about 100 pounds. Well, mom doesn't want the thing to move up and down. So she has to adjust her position to counter the torque provided by the child. Now, what do you mean by a torque? Well, what you have here is a door, like this, maybe like this, like that. There's a door. There's the hinge point of the door, and here's a force going that way. Well, that force is going to cause a rotation of this door going in that direction. And that direction would be counterclockwise. CCW, counterclockwise. On the other hand, if the force is going this way, then what would happen is the rotation would be going that way, and that direction would be clockwise. CW clockwise, CCW counterclockwise. So what happens is the torque is the product of the force and the distance. So let's just suppose that this distance, well, let's say it's about maybe 2 meters, or let's say 2 feet. So the torque produced by the child would be 2 feet times 50 pounds. And that would be 100 pound-feet. Now, mom has to balance that out. So where would mom have to sit? Well, you were old child at one time, so you know that mom would have to sit closer. So what she does is she moves in a certain distance, let's call it X. And so her rotation has to balance out the rotation of the child. He's going to cause a rotation which goes this way. Mom causes a rotation going that way. Her rotation will be clockwise. The child's rotation is counterclockwise. So what happens in this particular case is that her rotation would have to be X feet times 100 pounds. And that has to be equal to the child torque, which is 100 pounds feet. And what we do is we divide both sides by 100 pounds. And what happens is the distance that you would have to sit from that center point, that rotation point, would be 100 divided by 100 would be 1 foot, 1 feet. And that's what we're talking about in this particular experiment. All right, you can cut it.